Hi, my name is Markus Plack and I will present our work on fast differentiable transient rendering for non-line-of-sight reconstruction. Our goal is to improve the reconstruction of objects that are outside the direct line of sight of an observer. The most straightforward scenario for such a technique is in automotive applications, where the knowledge of what lies around the next corner is invaluable. Existing approaches typically have one or more shortcomings, including lacking of a forward-inverse consistency, the missing ability to reconstruct normals, not being easily adapted to other environments, and long reconstruction times. Our work builds on a capable rendering-based approach, but reduces the runtime from hours to minutes. Let's take a look at how a measurement setup typically looks like. We have an observer that is equipped with a laser and a time-resolved detector. To measure the occluded object, we use a relay wall that is fully visible to us and the hidden object. Emitting ultra-short laser pulses towards the wall, we record echoes of the light after it has traveled to the object and back to the wall. Repeating this process for multiple points results in a transient image. For our forward model, we use the same simplifications of the image formation model as the original renderer. They assume that there are no interreflections on the object since they contribute little to the final image, so the light travels from the wall to one point on the object surface and directly back to the wall. They also simplify the integration of circular segments. For each triangle, the radiance is assumed to be constant over the whole surface and computed at its centroid. To temporally distribute the returning light, a splatting function based on the distances of the triangle vertices is used to splat it into the corresponding bins of the transient image. Summing over all triangles and performing a binary visibility check results in the full model. Different from the baseline approach, we replace the central differences with a manual computation of the derivative and use it to backpropagate our loss. For efficiency, we implement all of this directly in our optics-based visibility programs. This means that we do not need to keep the number of parameters low and can optimize other, more complex scene representations. We also include the option of optimizing the albedo of the surface. Naturally, the image formation model does not cover all possible effects, even though it is physically plausible, as demonstrated in this example. This can quickly lead to low-quality reconstructions of measurements for optimization-based approaches such as ours. To solve this problem, we propose to use a neural radiance field type network to capture any unknowns and optimize it along with the scene representation. Using the spatial coordinates of the wall positions and the time as input, the network produces a background image that we add to the rendered transient. This improves the reconstruction significantly. Let us first take a look at the speed improvement compared to the baseline approach, where both methods use Gaussian blobs as a scene parametrization. You can see that our method gives a decent reconstruction early on and is close to optimal after 10 minutes. Increasing the playback speed, we can see that the baseline yields a recognizable result only after a few hours. Next, we show the reconstruction of the bunny from a high-quality transient rendering using a depth and albedo map representation. We compare our result to reconstructions from various other methods and find that our approach improves both coverage and accuracy compared to the state-of-the-art. For more results, applications, and details, please see our poster or paper. And if you want to try it out for yourself, we have the code, including all examples, online.